In this video, we'll talk about bridges, which is our gateway to trees. So a bridge in a graph, this is the analog of a cut vertex, but for edges. It's a cut edge, but we just call it a bridge. So what I mean by that is an edge, E equals UV. So sometimes we'll just, when we're talking about edges, this is pretty common to just give a name to the edge rather than specify the vertices of the edge, just call it E. So an edge in a connected graph whose removal disconnects the graph is called a bridge. So let's take a look at this graph here and identify the bridges. So which edges would disconnect the graph if you, which edges whose removal will disconnect the graph? So V4, V5, if I removed this edge, I'd be left with V4 as a component and then the rest of the graph as a component. So that would disconnect the graph. Same with V5, V6. So let's see, V4, V5, V5, V6 are all edges. Notice none of the edges in this block are edges, or are bridges. None of these edges will disconnect the graph. V7, V11 is a bridge. Again, here we have another block. None of its edges are bridges. But V8, V2 is a bridge. And it looks like that's all of the bridges. We grabbed all the bridges there. So these are all the bridges of this graph. Again, this is the analog of cut vertex. So for vertices that disconnect the graph, we have cut vertex. For edges, we have bridges. Both disconnect the graph, but they're different elements of the graph. All right, so the first thing to point out with a bridge is notice every edge here that wasn't a bridge lies on some cycle of the graph. So for instance, this edge V6, V7 lies on some cycle of the graph. Similarly, for every other edge that's not a bridge, we can find a cycle that contains it. And so this is a useful characterization for bridges. An edge E in a graph G is a bridge if and only if E lies on no cycle in G. So let's go ahead and prove this. Actually, before I do this, let's talk strategy a little bit. If I want to prove the forward direction of this, I'd be showing an edge E is a bridge, implies that E lies on no cycle in G. But we're actually going to work with its contrapositive. So this is equivalent to E lies on a cycle, on some cycle. There exists some cycle that contains E. Implies that E is not a bridge. That is, G minus E does not disconnect the graph. So we're actually going to prove the contrapositive of the forward direction. We're also going to prove the contrapositive of the converse. That is, so the original converse here would be if E lies on no cycle of G, then E is a bridge. I'm going to turn it around. I'm going to use the contrapositive again. This is equivalent to E is not a bridge. Implies that E lies on a cycle. So we're going to prove both of these statements, the contrapositives, to prove this. Working with the contrapositive here gives us a little bit more to work with. So let's prove it. I'm actually going to do the backwards direction first because that's what the book does. So I'll assume that E is a bridge of the graph. And actually first, it's okay to assume, we can assume that G is connected. Otherwise, we would just look at a connected component, and we might as well just consider that as our graph. That G is connected. Otherwise, yeah, we'll just focus in on a connected component of it. So let E equal UV be an edge that is not a bridge. Then G minus E is connected. So what's the situation look like? So I have this edge between U and V. It's not a bridge, so when I remove it, I'd have U and V, I'm still connected, right? Connected. So by definition of connected, there exists a UV path. Since this exists in G minus E, this path does not contain E. So there exists a UV path in G minus E. Hence, there is a UV path in G not containing E. Then this path together with E produce a cycle. Right, so I remove the edge, I look for a path between U and V. I'm guaranteed to find that because the graph is connected. And then I look for this path again in G minus, or in just G, and that gives me a cycle containing U and V. And in particular, a cycle containing the edge E. And that proves the backwards direction. Right? I've shown that there's a cycle containing E. E lies on some cycle. So now we'll start with the assumption that E lies on a cycle. Forward direction. Suppose E equal UV lies on a cycle of G. And the claim is that, so I want to show, claim G minus E is connected. Now, since UV lies on a cycle of G, again, I have U and I have V, there's some other path between U and V that does not contain E. So there is some path, what do I want to call this one? Let's call it P prime, path P prime in G that does not contain E. All right, that'll be useful. And I want to, so I want to show that G minus E is connected. So I want to show that any two vertices of G minus E, there's a path between them. So I'll just remind ourselves, want to show, given two vertices, x, y, in the vertex set of G minus E, and G minus E, we can find an xy path. But I want you to remember back to an earlier theorem that says if we can find an xy walk, then we can whittle it down to an xy path, right? That contains all the same edges, or that's contained in the walk. XY path. So how do I find this XY path? So I give myself these two vertices, X and Y. Now, right? So if we know that G itself is connected, I'll say since G is connected, there is an XY path in G. So that's great. So if this XY path does not contain my edge E, then I'm done. If this path does not contain E, then it's a path in G minus E and X, and then we found an XY path in G minus E, and so G minus E is connected. So assume E lies on this path. So okay, so I have this XY path, and maybe up here is U and V, there's my edge E, and then I come down and I get to Y. So maybe this XY path contains E, and then when we remove E, we're left with a disconnected graph. That would be sort of the worst case scenario, but we're trying to show that that can't happen. So remember that we can find this path P prime from U to V, right? I know there exists some path P prime from U to V. And so what I could do is I could go X to U, take this path to V, and then go to Y finally and get my XY path. I have to be a little bit careful though. The way I've drawn this, all these vertices are distinct, but it's possible that this UV path contains some vertices in this XY path. And so I can't necessarily say this is a path from X to Y, but I can certainly say it's a walk. So let's see. I'll say but, or I'll say let's let Q be the XU or XV subgraph of maybe I should call this path something, XY path, let's call it P. We haven't used P yet. So let Q be the XU subgraph of P subpath. And let's let Q prime be the YV subpath of P. Then Q together with P prime, remember, was my path from U to V, P prime and Q prime produce an XY walk in G minus E. And then I'll invoke this theorem. That was theorem 2.1. By theorem 2.1, there is an XY path in G minus E. So maybe some of these vertices are not distinct, but that's okay. I can at least find an XY walk, and by theorem 2.1, I'm guaranteed to find an XY path. And so that means, so since X and Y were arbitrary, G minus E is connected, i.e. E is not a bridge of G. And that's what I wanted to show. Remind ourselves what we wanted to show. We were proving the forward direction here. We started with the assumption E lied on a cycle, and we showed that it was not a bridge. All right, that's theorem 3.10. It's a nice characterization of bridges. See you next time.